Okay, let's move on. I start the timer.
So thank you, Nina, for the introduction. So thank you very much to the organizer for inviting me to this very nice conference. So it's the first time for me in India. So it's a pleasure for me to be here. Today I would like to talk about quantum fluid of light. And I would like to try to show you that it is possible with these systems to study topological excitation, quantized vortices and dark solitons. And also, as Iacopo has already explained, also to try to simulate astrophysical objects like, for example, black holes. So, okay, in our lab in Paris, we have two different platforms for studying quantum fluid of light. The first one is in a cavity geometry, and here we study polariton quantum fluid. And the other one is in a propagating geometry, and we study the propagation of a laser beam in a nonlinear medium. In this case, is a hot rubidium vapor. Okay, the outline of my talk will be the following. I will start with polaritons, so that I will introduce the system. Then I will show how it is possible to generate and control the propagation of topological excitation, exploiting a bistable regime, which is a typical regime that we can achieve in a polariton fluid. And so then I will show how with this polariton fluid is also possible so to build up an experiment to simulate black hole, hopefully to observe Hawking radiation. And if I have time, in the last part of the talk, I will describe our recent experiment in a hot rubidium quantum fluid of light showing quantum turbulence. Let's start with polaritons. So the system that we are investigating is a semiconductor microcavity. So we have a quantum well here between two Bragg mirrors. So this system is equivalent to a Fabry-Perot cavity of very high finesse. Polaritons are quasi-particle, half light, half matter, that comes from the strong coupling between exciton and photons in a microcavity. So then photons that are confined in the cavity, due to the confinement, acquire a light mass, an effective light mass. And on the other hand, the exciton interact non-linear each other. So then polaritons that are linear combination of exciton and photons inherit both of these properties of the component, of the two components. So then polariton have a light mass, effective light mass, and interact each other. So all in all, polaritons are described as weakly interacting composite bosons, and they are very well suited to study bosonic quantum effect. And in particular, I have reported here some of the most celebrated examples. So here, of course, the observation of polariton Bose-Einstein condensation in 2006, but also coherent propagation of polariton, the observation of long-range order phases, and superfluidity and Cherenkov regime in this fluid. But it is also possible, of course, to observe topological excitation in this polariton quantum fluid. One way is to use continuous wave non-resonant excitation. In this case, we have a polariton condensate, and the topological excitation are formed spontaneously in this polariton condensate. It is possible to observe quantized vortices, but also vortex lattices and so on. And it's also possible to use another experimental configuration in order to generate topological excitation, in particular to exploit the interaction of a polariton fluid with an obstacle. This was an experiment that we did some years ago in collaboration with Daniele. So here the polariton fluid is created by pulsed excitation, and during the propagation is interact with an obstacle, here created by another laser, and in the wake of the obstacle, it is possible to observe the nucleation of vortex and anti-vortex pair. Of course, the topological excitation lifetime and then the propagation is limited by the polariton lifetime that we standard microcavities of the order of, let's say, 15, 20 picoseconds. With the most advanced cavity now, it is possible to have a Polyton lifetime of the order of 100 picoseconds. Also, it is possible to generate topological excitation using continuous wave resonant excitation. And we have worked a lot with this kind of technique because it allows to have a very good control of the fluid phase and the fluid density. And then also in this case, we can observe vortex lattices, vortex rings, but also dark solitons and half soliton in case of spinor Polyton superfluid. There is a problem with this technique, which is the fact that also in this case, the propagation of the topological excitation is limited by dissipation. Because Polyton relax emitting photon that escape from the cavity, and then the Polyton density is decreasing. Here in this slide, just to have an idea of how it is possible to generate topological excitation in hydrodynamic wave by the interaction with the defect. So we have the polariton flow in this direction. This is a big defect. We have to consider spatially extended defect with a size which is larger than the healing length of the fluid. And of course, basically due to the conservation of the flow, we have an acceleration of the fluid in the vicinity of the obstacle, around the obstacle. And then the currents that are formed in the wake of the defect can give rise to turbulence and the observation of quantized vortices, dark solitons. For example, like in the water. No? But there is a point which is crucial with the continuous wave excitation scheme, because what is happening here when we excite our microcavity and we create a Polyton fluid in a resonant excitation, basically we fix the phase of the fluid, which is a copy of the phase of the laser. So then if we pump with our laser, which has a flat phase profile, of course, we cannot observe any topological excitation. Then we have to use a trick. We have to pump only in this region. This is the obstacle. The flow is in this direction. So then during the propagation, the Polyton fluid will interact with the defect, but in this region, we do not pump directly the microcavity, because otherwise we fix the phase. In this case, without pumping this region, the phase of the fluid, which is flowing in this region, is free, and then we can observe the nucleation of defect. But of course, here we don't refill our fluid with fresh pump, and then the density of Polyton decreases, and then the propagation is limited. This is the main problem of this technique. This is an experiment that we have done, the first experiment in which we have demonstrated the quantized vortices and solitons. So the idea is the following. We have a large defect here, large obstacle of the order of 15 micron, which is much larger than the healing length. And we can tune the polariton density. Tuning the polariton density is equivalent to tune the speed of sound in the fluid, which is proportional to the square root of the polariton density. So then here in this row, in this column here, we have a ratio between the speed of fluid and the speed of sound. It is very small. So the fluid is deeply subsonic. And then there are no excitation that can be generated in the wake of the defect. Here, the phase of the fluid is regular, it's very flat. This is another advantage of our system, because we can detect and measure the phase of the fluid in a very simple way, just making an interferometric measurement. So we can see here that the interference fringes are very regular. This means that there are no phase defects. This is the superfluid case. Then we can decrease the polariton density, we increase the Mach number, this ratio here, and we start to see the appearance of topological excitation. In this case, we have quantized vortices. We can see here in the interferogram the presence of forks. Okay, so the forks here is the experimental signature that we have here in this point, the quantized vortice, because the phase is around this point is changing by 2 pi. Okay, so but then we can also further decreasing the polariton density, we can enter a different regime in which we have no vortices but dark solitons. We can see 2 dark lines in the wake of the defect with a characteristic phase jumps, which is equal to pi, and these are so-called dark solitons. But as I already said, the very big problem with this technique is that we have a short propagation due to the dissipation. We pump only here, then the flow of the polariton goes in this direction, but due to the dissipation, after, let's say, 40 micron, the polariton density is very low and we have no more signals. Okay, so then how it is possible to solve this problem and to enhance the propagation distance, for example, of dark soliton or vortices? So the idea is to exploit a specific feature of the polariton system when it's pumped in resonance. So in particular, in the case of resonant pumping, the dynamics of the polariton fluid is described by this generalized Gross-Pitayevsky equation. We can recognize the standard terms that are also used to, so in the standard Gross-Pitayevsky equation used to describe the equilibrium Bose-Einstein condensate, atomic condensate, so the kinetic energy, the external potential, which is used in our case to model the presence of an obstacle. Here we have the nonlinear interaction term, and here we have the two additional terms, which are the losses, because polariton relax emitting photon that escape from the cavity, and the pump, okay, the resonant pump, which refill the system to have a steady state. The steady state solution of this equation exhibits bistability. So this is not surprising because, as I already said, the system is equivalent to a Fabry-Perot cavity with a nonlinear medium inside. And this is well known that this kind of system can exhibit bistability. So we have a bistability, and the idea is indeed to exploit this bistability in order to enhance the propagation length of the generated topological excitation. This was discovered numerically by Simon Pigeon some years ago. So we have here a typical bistability curve in the polariton system. This is the polariton density as a function of the pump intensity. And we can see that we have free region, no? Because we have a low density region. And in this region, of course, the nonlinear interaction are negligible. So then nothing interesting happens in this region. Here we have a region with very high density, but in this region, the phase is fixed by the laser. And then we cannot observe topological excitation. And then there is the bistable cycle here. And what is numerically demonstrated is that if we work on this region in the bistable cycle, we can have high polariton density without phase fixing, and then in this case, the topological excitation can be observed. And then we have changed the configuration of our excitation scheme in this way. So then we pump our microcavity with a very large spot, elongated spot like this. Here we have what we have called pump, but so all this is the pump laser. Here, the intensity is very high, is above the upper bistability limit. So in this region here, we fix the phase of our fluid. We generate a fluid which is propagating in this direction. But then when the fluid is approaching the obstacle, we can see here that the intensity is decreasing. And in particular, around the obstacle and in this wake, the intensity and then the polariton density is lying here in the bistable cycle, and then here the phase is free to move, is free to evolve, and then we can observe here in this region the formation of topological excitation. This is interesting because in principle the only limit that we have on the distance, the propagation distance of this topological excitation is given by the size of the spot that we can is not linked to the polariton lifetime. And these are the experimental results. So here, in this case, we have generated a vortex stream. These are numerical simulation. Here we have a time snapshot. So the defect is here. The flow is in this direction. And we can see the generation, the nucleation, continuous nucleation of vortex-antivortex pair. Of course, in a time-integrated experiment, what we expect to see is just a dark line because we cannot resolve the vortex-antivortex generation. It is indeed what we have observed in the experiment. The important point here is that now the propagation is very long, more than 100 micron, which is much longer than the distance that the polariton could propagate due to the lifetime. Okay, so, and this can be also used to enhance the dark soliton propagation. In this case, we can generate dark soliton, parallel dark soliton, up to, with propagation distance up to 150 micron. Up to now, what I have shown to you is our experiment in which we exploit the interaction of the polariton fluid with an obstacle. But the fact that we can control the phase of the fluid allow us also to imprint directly the polariton, so the topological excitation that we want to study. For example, in this case, we have imprinted dark soliton directly on the fluid, still exploiting the bistable regime. So in this case, for example, we shape the phase profile of the pump using a spatial light modulator in this way. So we can have here we have here a phase jump of pi. So then in this region here, we inject two dark solitons. We are working here in high density regime. So what we imprint on the fluid is exactly the copy of the phase profile of the pump. We can see here, we have this phase jump here, and in the density we see two dark solitons that disappeared when the phase here became flat. So then here, in the high density regime, the phase of the pump is copied exactly onto the fluid. But we can also use the property of the bistable region in which the phase is free to evolve. And then in this case, the soliton that are generated here in this region of high density propagate then through the bistable region for very long distances. So this is an interesting technique because allows to imprint directly solitons that can be studied. It's quite flexible, it's scalable because we can, for example, create in a controlled way soliton arrays. We can also, of course, create solitons with the transverse speed, with the speed in the transverse plane, which is not zero, so then they collide at some point. And then it's quite interesting to study in a controlled way soliton interaction. We can also study the snake instabilities with this technique because yeah, we can shape the phase and the intensity profile of the pump. So this was an experiment that we did in collaboration with Guillaume Alpuech and Dimitri Sholniskov at the University of Clermont. The idea is the following: we pump the fluid at normal incidence. So in this case, we have no flow. The fluid is created at rest. No speed in the polariton fluid, and we have two high intensity regions, P, and in the middle a bistable region, S. Okay, what we expected to see from the theory is that dark soliton can form in this channel inside the two high density region, but of course, due to the fact that this fluid is at rest, these solitons are unstable against transverse instabilities, and then they break in vortex, anti-vortex, and in particular, steady-state vortex, anti-vortex chain appear. And the shape of this chain depends on the relative density, the relative intensity in the region P and S. We can see that, in principle, it is possible to observe anti-symmetric vortex anti-vortex chain or symmetric vortex anti-vortex chain. We did the experiment. We create this kind of pump, so with two high density region and a channel in the middle. We have the same phase between the two high intensity region, and then of course to accommodate the global phase, so we can observe only an even number of solitons. In this case, 4, increasing the width of the channel. We increase also the number of the observed solitons, 6 in this case, and then we start to see the snake instability here, the onset of the snake instability. Okay, so then it is possible also to play with the phase jump. If we have now two high density region with a pi shift between them, of course, the global phase jump has to be conserved, and then we can observe only an odd number of dark solitons, 1 or 3, depending on the power that we set in the channel, in the inner channel. And then finally, we have observed the formation of these symmetric chains of vortex anti-vortex in closed channels. So we have this channel which is surrounded by a very high density region here, and increasing the density in the channel, we can decrease the healing length of the fluid, and then we can increase the number of vortex anti-vortex pair that we observe. We can see clearly here 4 and 5, and this is of course in agreement with the numerical simulation. If the intensity in the channel is increased too much, so basically we fill the channel, and then we have no more soliton or vortex. Okay, so this was for the topological excitation in polariton. So we have developed an all-optical technique to generate steady-state topological excitation and to control the macroscopic propagation of this topological excitation. We have also developed a all-optical technique to imprint dark solitons. And finally, we have observed, we studied the transverse instability, observing the formation of vortex anti-vortex chain. This was for the, let's say, topological excitation in polariton. And now I would like to show in the last minutes that I have that this system is also interesting in order to try to simulate, so to make an analog physics and to simulate, in particular, black holes. So this is a cartoon that Iacopo has already explained. So the idea is that we want to build up an experiment in order to study the behavior of acoustic wave in the vicinity of an analog black hole, an acoustic black hole. So the idea is to use this waterfall configuration, and as Iacopo already explained, so we have here the equivalent of a acoustic horizon, because this fluid is transonic. We have a region here in which the fluid is subsonic, and here is supersonic. So then the volume of excitation on top of the fluid that are represented here by this fish cannot cross this point, which is the equivalent of an horizon. Okay, so then when we have this horizon, the quantization of the sound wave tell us that vacuum fluctuation has scattered the horizon, and normally we should have this Hawking radiation, and the idea is that in this analogous system it is possible to detect inside the outside the black hole, and then see the quantum correlation or entanglement. So how to build up this and set up this kind of experiment in polyton fluid? So to create an horizon is possible in polyton because we have a very precise control of the speed of sound and the speed of fluid. The speed of sound is controlled via the intensity of the laser, because the intensity of the laser controls the density of polyton, and the speed of sound is proportional to the square root of the polyton density. So then we can control the density and then control the speed of fluid, the speed of sound, sorry. And on the other hand, the speed of fluid is given by the gradient of the phase of the polyton fluid that, as I already shown you, it is possible to control with the pump laser. So we can imprint the phase of the laser on the fluid. So then it is possible to create two regions, like these are experimental results, in which the fluid is subsonic, the speed of sound is larger than the speed of fluid, and then we have in the other region of space, this is a one-dimensional polyton flow. Here we have a supersonic fluid. Here, then we have the equivalent of the horizon. Once the horizon is presented in the fluid, so is constructed in the fluid, what we can do, so what we want to do now is to study the Hawking effect at the horizon. So observing the scattering of an acoustic wave at the horizon. So the idea is to start with a stimulated experiment. So we send a probe here, which create an acoustic wave which is traveling toward the horizon, and then we observe the scattering of this acoustic wave. The reflected part of the acoustic wave gives the Hawking radiation. The transmission is the so-called partner radiation. And these are the volume of dispersion relation for the subsonic and supersonic region. And we can see here that the ghost branch is pushed toward positive energy due to the Doppler effect. So then if you put the probe here, we generate the partner here, which is transmitted, and the Hawking radiation, which is reflected. So this is quite nice because we can we know exactly in the frequency, which is fixed by the probe, and the wave vector of the radiation and partner mode that we have to detect. So the theory, of course, predicts that these two modes, Hawking and partner, are entangled, and the signal should be strong enough to be measured with quantum optics technique. We plan to use homodyne detection to do these measurements. For the moment, the situation of the experiment is the following. So we have an horizon, we have a subsonic region and the supersonic region. We are able to measure the dispersion relation, Gogolubov dispersion in the two regions. So this is with a technique that we have recently developed. And then the next step, as I said, send the probe, identify and separate in the momentum space the two modes, working and partner, optimize the detection setup in the stimulated emission, so then switch off the probe, and then in this case, we are in the spontaneous emission, and use homodyne detection on conjugate quadrature of the field, and hopefully verify the entanglement using, let's say, some criterion like one criterion for entanglement. Yeah, so this is the program. I don't know if I have time to 3 minutes, so okay. I can show the last part of the talk. So in this case, we use the different platforms. So we use the rubidium, the hot rubidium vapor platform. The system has already been introduced yesterday morning. So we use, so we study the propagation of a laser beam inside a nonlinear medium, which in our case is a hot rubidium vapor. The equation that describes the propagation of this beam in the nonlinear medium is the Schrödinger nonlinear equation, which is formally analog to the Gross-Pitayevsky equation. We have a kinetic energy, external potential, and the nonlinear interaction. So this system allows us to have a quantum fluid of light in the transverse plane orthogonal to the propagation direction. There is a difference, an important difference here, because you can see here that the derivative is with respect to z, not with respect to the time. So here the propagation distance is the equivalent of the evolution time. What we have done, sorry, in this setup is to study the turbulence that can be generated when we create two counter-propagating quantum fluid of light in the cell. So this is quite straightforward to do. We have a laser beam which is sent on a spatial light modulator. So we modulate with a spatial light modulator. We create two plane waves that impinge on the cell with an angle, a given angle. And in the transverse plane, of course, this is equivalent to two counter-propagating quantum fluid of light that collide. And we can see that at the beginning of the cell, so at the end, and the input of the cell, we have just regular interference, the fringes. But then, during the evolution in the nonlinear medium, we can develop quantized vortices, soliton, and turbulence. Here we have the density image. Here we have the phase image. Also, in this case, we can directly image the phase, so measure the phase of the fluid with an interferometric setup. Here, what we have verified is the emergence of isotropy in the density spectrum. This can be done quite easily, making the fast Fourier transform of the image, here of the density image, the area space. And then we have the density spectrum. We have traced here the density spectrum for the for the wave vector in the x direction and in the y direction. And we can see that at early time, there is a strong anisotropy due to the fact that we have a forcing frequency, which is fixed by the angle that we impose at the input. But then, during the evolution, we have so we have the emergence of an isotropy, and here the two distributions are superposed for all the wave vector. Then, of course, thanks to the fact that we have the phase, we can calculate also, we can extract the the fluid velocity field, and then measure the density weighted velocity. Using the Helmholtz decomposition, we can separate the fluid velocity in compressible and incompressible part. And at the end, we can reconstruct the kinetic energy spectrum, and then we can see the different power scale law, K power 1, -3, and -5/3 in the intermediate range of spatial frequency, as it is expected by the theory. Okay, just to show that this is an interesting system, quite flexible. For example, we can also study vortex collision. Here we can inject two vortices at the input of the cell with a fixed distance R. And I have two videos. I don't know if I have the time to show.
I think we can see the videos.
Okay, see, this is the first is for the collision of two same sign vortices. So we can see that they start to approach, and then they start to rotate one around the other. And at the end, they stop to move, because indeed so we have a problem with the saturation of the nonlinearity. So then we cannot, for the moment, increase a lot the time of evolution. And in this second case, we have an opposite sign vortices, and then what we see that they merge, so eventually they annihilate. Okay, so this is all what I would like to show you. And before to conclude, I would like just to thank all my collaborators, in particular, so Quentin Glorieux for the experiment on the rubidium vapors, Maxime Jacquet, Kevin Falk, and Kilian Guerrero here for the experiment on the black holes. Also Miran Baker, which is who has worked on this collision of vortices and turbulence in the fluid of light. So thank you very much for your attention. Thank you.
Thank you very much. Questions?
So thank you very much. I have a question that shows my completely ignorance about this. So you say that automatically you have a quantum fluid of light, just injecting a laser beam in this vapor
Yeah,
vapor
because
cell, but
so
why?
no, automatically it depends on the nonlinearity that you have. So you have to play with the nonlinearity,
So, okay.
and then so we can control the nonlinearity in two ways. So one, playing with the temperature of the cell, because in this case we increase the density. Typically we work around 120 degrees Celsius. And the second is the fact that we can tune, of course, the tuning with respect to the resonance, the atomic resonance. In choosing the detuning, we can also change the sign of the nonlinearity. No?
Okay.
You can have repulsive or
Okay.
attractive and so on. In this case, of course, we are repulsive. And typically we work detuned with respect to the D1 line of about, no, T2 line, D2 line about 5 gigahertz.
Yeah, but my question is also concerned to what Martin is doing in this experiment. So which is the comparison between the two kind of experiment?
The system are different in the sense that in the case of polaritons, so we are we have a cavity system, and the point is that the temporal evolution is very fast. So then we have worked a lot in stationary steady state. So in steady state, so then in this case, we can observe some interesting phenomena, but we cannot follow the dynamics, for example, of the vortices and so on, because for this we need a very high temporal resolution because the Polyton lifetime is of the order of picosecond. And then it is not possible to follow, for example, a vortex directly. In the next talk, there is Clément will show a technique that is they are developing in order to have a very nice resolution. In the case of the propagating geometry, we have no this problem because the evolution time is the distance. So then indeed we can follow, for example, the dynamic of the vortices, just changing the effective interaction time that we can control, changing the nonlinearity. Okay, because the effective time is the propagation distance divided by the effective nonlinear length. Is the main difference.
Right. So I will have one question of my own, a very naive one, for the very last part where you have shown this like rotation of vortices or merging of the opposite sign vortices. If we compare them to gravitational objects, like the black hole merger, could you compare it to it? Do they emit anything?
I think that it could be interesting to look at this, because when they are merging, normally we see some acoustic wave, which is the fluid is perturbed by this. So then I don't know.
Do they accelerate actually when they?
For the moment, we have no. It's just preliminary result, but I think that the system is quite analogous to this merging of black holes. Yeah.
Right. So let's thank Alberto again. Thank you very much.
Thank you.